All right, so I'm going to go ahead and start back up, and we're going to go through another technique on basic exploit writing on Windows. Those of you who hear me streaming right now, just so you know, I'm in Las Vegas at Caesar's Palace in a classroom. We're doing a section on introductory Windows exploit development before we get into more advanced stuff. So we just got done doing a basic Stack Overflow on Windows 11 against a third-party application. And it was possible to be able to exploit it because there are non-rebased modules that come along with this application, which is a challenge for Microsoft. They can't force third-party developers of applications to ensure that when they compile their libraries that they use dynamic rebase, which would allow those libraries to participate in randomization each time you reboot the Windows operating system. There is, of course, that mitigation called mandatory or force ASLR, and that's going to ignore whether or not the library was compiled with dynamic base flags, and it's going to have it participate in rebasing an ASLR anyway. For most applications that are written properly, it shouldn't hurt anything. However, if there are any static addressing dependencies within the app, within the application, for a memory address within one of those third-party modules, then that's going to break the application. And as we discussed, most organizations will leave whatever exploit mitigation settings are there by default, like on Windows 11, at their base. Whatever was on when they built that system, that's what's going to stay. That's because there are over 25 now mitigations in user land that you can enable or disable as part of Windows Defender, Exploit Guard, or Exploit Protection, whatever you want to call it. Some of these mitigations Microsoft turns on when they feel that enough systems, enough applications have more recent processors or whatever else that applications are developed properly, like data execution prevention. That's one of those ones where it should not break any applications, and it's a system level enforcement. But when you talk about things like Exploit Guard, there are all these granular settings that you can make per application in audit mode or active mode, and some of those do carry overhead and could break applications. As I mentioned earlier, I remember the simulate execution flow anti-ROP protection would break Chrome and Firefox when I ran it, because when it goes to simulate instructions after a return, it thought it saw indications of a potential return-oriented programming style attack. So you have to disable that. And administrators don't want to do the screen test and just start enabling mitigations and hope for the best. You have to go through and test each application with each mitigation to examine the overhead associated with it, as well as whether or not it breaks anything. And that's just a lot of extra work. Historically, the technical details around how these mitigations work were lacking. Thankfully, a couple of years ago at the Blue Hat conference, they released a bit more documentation on it. A lot of them you have to go through and reverse engineer and debug yourself to understand how they actually enforce the mitigations. I've done a couple of those streams on the Off by One channel where we walk through looking at mitigations like EAF for export address table filtering or do not allow child processes. Some of these enforcements are in user land, some of them are in kernel land. So you've got to have a kernel debugging set up. My point again being that a typical Windows administrator does not have the time and maybe not the interest or skills to go in and do kernel debugging to try and figure out how a mitigation works. And some of the mitigations actually require that a developer understand the mitigations to be able to opt in or out at the thread level. Another example of a mitigation we talked about was disable Win32k syscalls, where if you have an application that does not have any GUI thread requirements, you can reduce the attack surface by disallowing access to the Win32k syscall table and leave only the NT syscall table accessible. All right, so let's move on. And the Stack Overflow that we just did allow you to do a return pointer overwrite and get control that way after the epilogue finishes and we ret. A lot of times though, like if you go out to exploitdatabase.com and you do a filter for Windows overflows, you'll see that the majority of them have SEH in the title, which means, of course, structured exception handling. This ability to overwrite handlers on the stack only applies to 32-bit processes, because in 64-bit, they changed the way that structured exception handling works a bit. So it's no longer sitting there on a stack at a terrible location, allowing you to overwrite it. The problem is that even though in the majority of cases with something as basic as a stack overflow, you are overwriting the return pointer to get to the structured exception handlers, you'll never get control via the return because you never make it to the epilogue. Something that's happening earlier in that function after you have some memory copy operation that allows you to overrun a buffer, again, some code between that point and the remainder of that function until you get to the epilogue causes an access violation, which means even though you overwrote the return pointer, you never actually get to the return instruction. Therefore, the structured exception handler might be the only way that you're able to gain control. So if we look at a slide real quickly, like we're saying, why do it this way too if we can already overwrite the return pointer? And this gives you an example of some code that might cause a problem. Imagine if you sent in like 500 A's into the buffer to get to the return pointer overwrite. And then after you do that, before you get to the epilogue, you get instructions like the ones on the slide. The first one says, move into EDI, dereference the stack pointer offset 8 or plus 8. So whatever's stored on the stack plus 8 from the stack pointer location, we're going to dereference that and load it into the EDI register. Well, since you wrote a ton of A's, guess what's going to load into EDI? 41414141. Then the next instruction says test whatever's at the address stored in EDI against the number 8. That's going to cause the access violation right there, because it's going to try to go to address 41414141, which is not going to be mapped from virtual to physical addressing in the page tables, and that's going to be your access violation that says write access or read access violation, which means that you never are now going to make it to the return to get control via the return pointer overwrite, and your option is going to be to go after the exception handler on the stack. So this just shows you, it's not the greatest image, but it just shows you the NSEH pointer. So remember, when a thread experiences an access violation, you're going to go to FS offset 0 in that thread's thread information or environment block, which holds the pointer to the first handler on that thread stack. And each location on the stack where the handler is, there's 2 double words. One is the NSEH pointer that says, here's how you get to the next handler on this thread stack if the first handler couldn't handle the exception. And then directly below that is the pointer into a DLL where the handling code is. And it's going to say, can you handle that exception? Yes or no? If no, we have a callback pointer, which takes us back to the NSEH position on the stack. We walk it to the next stack position where the next set of handling or handler code pointers are. That's how it's supposed to work. So obviously, if we overwrite that like we see here, the NSEH pointer has 41414141, and the SE handler, which should point to a DLL's handler code, says 42424242. So if we were to pass the exception, we're going to get control of the instruction pointer this way. So what happens when you pass the exception? There's something called the establisher frame. Far away on the stack in the area you have control, there's going to be a small stack frame set up for the handler. And it's a static just fact that at plus 8 from the stack pointer, at the moment in time you cause an exception and try to go to the first handler on the list, at plus 8 is the callback pointer to the NSEH position in case that handler can't handle the exception. So it needs to know how to get back home to the stack so it can walk to the next handler and try that exception handler as well. So what we're going to want to do, it's a common old technique. I guess you would consider this a ROP gadget. It's just a sequence of code that says pop, pop, ret. We're popping the first double word off the stack that the stack pointer points to. causes it to advance down to the next double word. We pop the second double word out the stack, leaving us at the third where the callback pointer is, and that's the one we return to. So we're now returning, which is giving us code execution on the stack, and we'll actually execute AAAA, which will be the opcode for increment ECX, increment ECX. That's pretty benign, shouldn't hurt anything. But then what's going to happen is it's going to try and execute the address you used to overwrite the handler, meaning the address where the pop ret was. It's going to interpret those address bytes as opcodes. This will often cause it to crash. You'll see that in a demo here in a second. So we'll need to use a little technique that allows us to jump over the old handler address or the handler address that you use for the pop ret and get right to your shellcode. This just shows you the pop ret. So we pop the first double word, pop the second double word, return. That causes us to go back to the NSCH position via the callback pointer, and we will execute 41414141. That just shows you what you would see in the disassembler window as you execute the increment ECXs. What we need to do, or what we will need to do, is set up a little EB, which means jump short in x86, followed by 06. That's your operand. And 06 means jump 6 bytes, because EB06 is 2 bytes. We're jumping 6 more bytes because there's 2 more bytes left in the NSCH pointer, double word, and then there's 4 bytes, of course, in the actual handler. We're trying to jump over it to get to our little NOP sled there if we need a NOP sled. You don't need a NOP sled in this at all, so it's just nice to show it during demonstrations for being able to see the patterns. All right, so let's jump in here and do this. So here is our old script that we used for the last example of doing a return pointer overwrite. And we know that if we send in 800 A's into this little playlist file and it gets opened by the application, it causes the buffer overflow. It's a very weak, sad vulnerability that's been reported to this vendor dozens of times, and they don't fix it. They don't care. Even the newer version that they came out with, they still didn't fix it. So if they don't care, then nobody else should care. So let's go ahead and bring up the binary, and we'll say later to the nag screen, let the app come up. And again, this is just, it doesn't matter what application we're using to demonstrate these techniques, because when you find this type of vulnerability, that's when you can apply these techniques. This is just our guinea pig to test with. So we're going to go ahead and we'll just jump and grab the pattern that we generated so we can see exactly how many bytes it takes to get to the structured exception handler. So let's go back and go to our folder that Mona created, grab that pattern, just copy it, close that out, go back to our script, and change the 700 A's to be the pattern again. Save it, run it, and now it's going to create a new file called blaze2.playlist file. Let's go back to that folder. And then we will go ahead and click on the folder icon, open playlist, click on the new file we generated now, but don't open it yet because we want to attach with the debugger. Again, the only reason we're using immunity is because Mona just works really easily in here. Otherwise, we'd be using x86 or x64 debug or WinDebug. Mona works on WinDebug, but this is just an easier debugger to use when you're just getting started. So we'll say attach. We'll click on Blaze, attach. Let me zoom out here for a moment. Once it attaches, we'll let it play and make sure that it shows as running. You can see it says running now at the bottom right. Thread just died, no big deal. Click on C for CPU to bring the active thread up. And now we'll go back over and open this file. All right, so the crash just occurred. Just like in the first example, we overwrote the return pointer, which is why we're getting this piece of the pattern inside the instruction pointer. But now we're doing an SEH overwrite. So if you go down on the stack and we page down a couple times, Make sure I'm not going too far. There we go. You can see that we also wrote the SE handler. So when a thread exception occurs and you dereference fs offset 0 from the tab, this is the address that it's going to hold. That's what we're dereferencing. So at this location is supposed to be the pointer to the next SEH record on the stack in case this handler below it can't handle the exception. We'd call back to here. We'd walk this to the next pointer on the stack and try that handler out. So this is the pattern that's going to show up in the instruction pointer when we pass this exception. So you can see we have an access violation. I'm going to hit Shift F9 in the debugger to pass the exception. And now you see another piece of the pattern shows up. So we'll grab this value, go down and say Mona pattern offset that value. And it says it found it at position 612. So 612 bytes is what it takes to get to the SE handler location. So let's validate that. So we'll kill the debugger, go back to our script, change this to A times 612, like it said, plus this is going to be the SE handler location. So we'll say hex DE hex C0 hex 80 hex DE, just dead code should be what shows up. We'll say plus. I'm just going to put hex 90 times 20 so we can see the pattern, and then plus just hex CC for a software interrupt times 20. So we see everything laid out nicely. So we'll go ahead and save this, and then we'll run it. Looks good. And let me zoom out for a second so I can start the application back up without being zoomed in. So we start up the application that's affected. We'll click on the folder icon and open playlist. Don't open it yet. Attach to it with the debugger. Attach Blaze. Once it gets done attaching, we will let it run and then open up the file. So let's go over and do that. Then we get the access violation because we overwrote the return pointer. So we're going to pass this exception. Before we do that, let's look down on the stack again to make sure our alignment's good. So there you can see we perfectly overwrote the handler with dead code. So when we pass the exception, that is what we should see show up in the instruction pointer. So let's pass the exception, Shift F9. And now we got control for a second time, this way with the SEH overwrite. Great. So here's where I want to validate and show you that this establisher frame that we talked about. Right now, the handler, it tried to call the first handler on the list that we overwrote. Remember the rule I said, that the stack pointer at that moment in time, +8, is where the callback pointer is stored. So if we right click on that and say follow and stack, see how it takes us right back to where the NSCH position should be? That is why if we do a pop ret, pop this out the stack, pop that out the stack, and return to this one, we'll get code execution on the stack. So the next thing we need to do is find a pop ret sequence, which is going to be super easy. Earlier, we used Mona to identify non-operating system DLLs that don't participate in certain mitigations like rebasing. So we already have that one. We're going to use configuration.dll. So we'll say Mona, SEH is the command, -m for module, configuration.dll. This is going to take 30 seconds maybe up to run, because it's going through all the executable code and looking for the opcodes that are pop return. And it's going to be hundreds of them most likely. So wait for the pinwheel to stop, click on the log window when it's done, and we should have a lot of addresses we can use. There it goes. So click on the log window. Now we can see we found 450 pointers just in that one DLL. So I'm going to grab the first one up here. Right click, we'll say copy to clipboard, the address. And now we're going to zoom out again and close everything up. So back to our script, we're going to modify it now. just so we don't have to write in little endian, we'll say import struct, and then create a little variable called SEH equals struct dot pack little endian, and then put the address in of the pop return. I'm going to grab that address because we're going to set a breakpoint on it to watch how things work. We're going to change dead code for the SE overwrite to our variable SEH that will be packed into little endian. And I want you to see why this is going to fail, because we have to do one more thing. So let's save it. We'll say run module, same thing as before. Repeat the steps, the annoying part of debugging GUI apps sometimes. Click on the folder icon and open playlist, Blaze 2, immunity, file attach, Blaze. When it attaches, click play. Give it a moment. And what we're going to do now is search for that address that we're using for the pop return. So Control G, paste it in. And there we can see the pop return. We'll set the breakpoint there. Everything looks good. And we'll open up our exploit now. So we open it, we get the access violation for overwriting the return pointer and access violation when executing an invalid address. Let's look on our stack. You can see that we have overwritten the SE handler with the address of the pop return. Everything looks good. We got the breakpoint. So let's pass the exception. So Shift F9, and we hit the breakpoint. We're at the pop return. Great. So what we're going to do is pop this off the stack. So single step, F7, pop that off the stack, F7, and now we're about to return to the callback handler. So if we right click on this to verify, follow in stack, so we're going to return to this address and execute this opcode as increment ECX. So let's let that return execute. And now you can see we've got the A's, increment ECX, increment ECX. Look at the problem though. It's going to interpret our address as opcodes, and unfortunately the last byte was C3, which is a return opcode. That breaks our attack. So what we're going to do is instead put EB06, Y06, because 1, 2, 3, 4, 5, 6 bytes gets us down to the NOP sled. I'm going to remove the NOP sled actually because we don't need it. It's just there for visualization. And let's do this for the last time. Close the debugger, go back into our script, and we have to subtract 4 bytes from our input because that gets us to the NSCH pointer, which is where the first 41414141 executes, the increment ECX. We're going to say hex EB for jump short, hex 06 bytes, pad byte. That takes us out to 1 double word to fill up the entire NSCH double word block, and then we'll have that. Let's go grab our shell code real quick so we get a shell, something interesting. So this will just pop a shell. So let's put that in here. We're good to go. Change hex cc times 20 to shellcode variable and save that. Going to grab that address again and we'll run this. There's an error in my syntax. What did I do? Something dumb wrong. Oh, I forgot to put a plus right here. All right, there we go. Start it up. Open playlist, Blaze 2, immunity, file attach, Blaze. Let it play once it attaches. And then let's look for that address again that we used. There it is, pop return. I'll set a breakpoint there. And then we're going to open our exploit. So open, cause the access violation. We pass it, so we get the exception. So Shift F9. We hit our breakpoint now. So again, we're at the pop return. So we're going to pop this off the stack, that off the stack, return to the NSEH location. So let's do that. Pop, return. And now we're returning to a jump short 6 bytes, which is going to let us hop over here. I forgot to remove the NOP sled, but whatever. There's our shellcode right here. So we'll take the hop right now, and now we got around the problem. And we let it continue. It slides down. Let me zoom out here for a second and let it go. And we should get a shell here pop up. There it is. So that's an easy one to do. The funny thing on this one, because this sometimes happens, so I'll point it out. We're going to run it outside the debugger to make sure it works. And when we do this, we get a good deal today because we get 2 shells for 1. And there we go. 2 shells. So double the execution for the same price. Why did it do that? Probably because it caused an exception after it popped a shell, didn't know where to go, called the same exception handler, repeated the same thing, and then punted. So I had a student recently who got a fork bomb against themselves. It was just like thousands of shells in a loop, and it DOSed his system. So pretty amusing. That is the gist of this exercise before we move into more advanced stuff. Like I said, this stuff is a rite of passage. We've been able to do this stuff for decades, and it's crazy that we still can do it. Shadow stacks and control flow enforcement technology will finally kill our ability to do this. Once Microsoft and vendors start turning that on by default, when enough processors are supporting it, because you have to have a new processor because it has a new register called the shadow stack pointer register, and it has to support different instructions and stuff. So Microsoft will turn it on for everything at default at some point, which will kill Stack Overflows finally once and for all. And then you have control flow enforcement technology where we have to deal with the end branch instruction that has to be every time you ret, the address you're returning to must be that of an end branch instruction directly below the call that you're returning from. That is the ROP killer, the return-oriented programming killer. So when we get there very soon, a couple years, I don't know, we'll obviously need to switch to jump-oriented programming, counterfeit object-oriented programming, and other ones, or just get away from that bug class, focus more on heap exploitation like we'll do as well. So obviously after this, you go into like try off by 1 exploitation. What can we do with an off by 1? Well, sometimes we can overwrite 1 byte further than we should and overwrite the size variable or value of a chunk and force it to go back to the wrong Tcache bin and stuff like that. We do things like use after free, type confusion, double fetch. You know, those are all the more advanced exploitation that we move into. Then we got to deal with the kernel mitigations such as, you know, VBS, hypervisor, you know, HVCI, lots of mitigations that the secure kernel enforces with Hyper-V. So cool. Go ahead and run through this lab, and then we will move on. For those of you on the stream, I'm just going to stop sharing now. And cool. Yeah, as you saw, I couldn't really answer any questions because I'm teaching this in the class, but feel free to use a comment on YouTube, and I'll leave a comment and I'll check it out there. We got a lot of great streams coming up soon. I'll post them up here shortly, and some cool stuff like custom shellcode generation kit and really neat stuff. Thanks.